In this video, I'd like to start talking about a second type of unsupervised learning problem called dimensionality reduction. There are a couple different reasons why one might want to do dimensionality reduction. One is data compression, and as we'll see later, a few videos later, data compression not only allows us to compress the data and have it therefore use up less computer memory or disk space, but it will also allow us to speed up our learning algorithms. But first, let's start by talking about what is dimensionality reduction. As a motivating example, let's say that we've collected a dataset with many features, and I've plotted just two of them here. And let's say that unknown to us, two of the features were actually the length of something in centimeters, and a different feature, x2, is the length of the same thing in inches. So this gives us a highly redundant representation, and maybe instead of having two separate features, x1 and x2, both of which basically measure the length, maybe what we want to do is reduce the data to one-dimensional and just have one number measuring its length. In case this example seems a bit contrived, this centimeter and inches example is actually not that unrealistic and not that different from things that I see happening in industry. If you have hundreds or thousands of features, it's often just easy to lose track of exactly what features you have. And sometimes you may have a few different engineering teams. Maybe one engineering team gives you 200 features, the second engineering team gives you another 300 features, and the third engineering team gives you 500 features. So you have 1,000 features altogether, and it actually becomes hard to keep track of exactly which features you got from which team, and it's actually not that hard to have highly redundant features like these. And so if the length in centimeters was rounded off to the nearest centimeter and length in inches was rounded off to the nearest inch, then that's why these examples don't lie perfectly on a straight line, because of round off error to the nearest centimeter or the nearest inch. And if we can reduce the data to one dimension instead of two dimensions, that reduces the redundancy. For a different example, again, maybe one that seems slightly less contrived, for many years I've been working with autonomous helicopter pilots, or I've been working with pilots that fly helicopters. And so if you were to measure, if you were to do a survey or do a test of these different pilots, you might have one feature, x1, which is maybe the skill of these helicopter pilots, and maybe x2 could be the pilot enjoyment, that is, how much they enjoy flying, and maybe these two features will be highly correlated. And what you really care about might be this sort of this direction, a different feature that really measures pilot aptitude. And I'm making up the name aptitude, of course, but again, if you have highly correlated features, maybe you really want to reduce the dimension. So let me say a little bit more about what it really means to reduce the dimension of the data from two dimensions, that is from 2D to one-dimensional or to 1D. Let me color in these examples slightly different colors. And in this case, by reducing the dimension, what I mean is that I would like to find maybe this line, this direction on which most of the data seems to lie, and project all the data onto that line that I just drew. And by doing so, what I can do is just measure the position of each of the examples on that line, and what I can do is come up with a new feature, z1, and to specify the position on the line, I need only one number. So z1 is a new feature that specifies the location of each of those points on this green line. And what this means is that whereas previously, if I had an example x1, maybe this was my first example, x1. So in order to represent x1, originally x1, I needed a two-dimensional number, or a two-dimensional feature vector. Instead, now I can represent z1. I can use just z1 to represent my first example, and that's going to be a real number. And similarly, x2, if x2 is my second example there, then previously, whereas this required two numbers to represent, if I instead compute the projection of that black cross onto the line, and now I need only one row number, which is z2, to represent the location of this point z2 on the line, and so on through my m examples. So just to summarize, if we allow ourselves to approximate the original data set by projecting all of my original examples onto this green line over here, then I need only one number, I need only one row number to specify the position of a point on a line. And so what I can do is therefore use just one number to represent the location of each of my training examples after they've been projected onto that green line. So this is an approximation to the original training set because I have projected all of my training examples onto a line. But now I need to keep around only one number for each of my examples. And so this halves the memory requirement or the disk space requirement or what have you for how to store my data. And perhaps more interestingly, more importantly, what we'll see later in the later video as well is that this will allow us to make our learning algorithms run more quickly as well. And that is actually perhaps even the more interesting application of this data compression rather than reducing the memory or disk space requirement for storing the data. On the previous slide, we showed an example of reducing data from 2D to 1D. On this slide, I'm going to show another example of reducing data from 3-dimensional or 3D to 2-dimensional 2D. By the way, in a more typical example of dimensionality reduction, we might have 1,000-dimensional data or 1,000D data that we might want to reduce to, let's say, 100-dimensional, 100D. But because of the limitations of what I can plot on the slide, I'm going to use examples of 3D to 2D or 2D to 1D. So let's say I have a data set like that shown here, and so I would have a set of examples, xi, which are points in R3, so 3-dimensional examples. I know it might be a little bit hard to see this on the slide, but I'll show a 3D point cloud in a little bit. And it might be hard to see here, but maybe all of this data maybe lies roughly on the plane, like so. And so what we can do with dimensionality reduction is take all of this data and project the data down onto a 2-dimensional plane. So here what I've done is I've taken all the data and I've projected all of the data so that it all lies on the plane. Now finally, in order to specify the location of a point within a plane, we need two numbers, right? We need to maybe specify the location of a point along this axis and then also specify its location along that axis. So we need two numbers, maybe called z1 and z2, to specify the location of a point within a plane. And so what that means is that we can now represent each example, each training example, using two numbers that I've drawn here, z1 and z2. So our data can be represented using vectors z, which are in R2. And these subscripts, z subscript 1, z subscript 2, what I just mean by that is that my vectors here, z, are 2-dimensional vectors, z1, z2. And so if I have some particular example, zi, well, that's a 2-dimensional vector, zi1, zi2. And on the previous slide, when I was reducing data to 1-dimensional data, then I had only z1, right? But and that's what the z1 subscript on the previous slide was. But here I have 2-dimensional data, so I have z1 and z2 as the two components of the data. Now, let me just make sure that these figures make sense. So let me just re-show these exact three figures again, but with 3D plots. So the process we went through was that shown in the left is the original dataset, in the middle the dataset projected onto 2D, and on the right the 2D dataset with Z1 and Z2 as the axes. Let's look at it a little bit further. Here's my original dataset, shown on the left, and so I had started off with a 3D point cloud like so. So where the axes are labeled x1, x2, x3, and so this is a 3D point cloud, but most of the data maybe roughly lies on, not too far from some 2D plane. So what we can do is take this data, and here's my middle figure. I'm going to project it onto 2D. So I've projected this data so that all of it now lies on this 2D surface. Okay, you can see all the data lies on a plane because I projected everything onto a plane. And so what this means is that now I need only two numbers, z1 and z2, to represent the location of a point on the plane. And so that's the process that we can go through to reduce our data from 3-dimensional to 2-dimensional. So that's dimensionality reduction and how we can use it to compress our data. As we'll see later, this will allow us to make some of our learning algorithms run much later as well, but we'll get to that only in a later video.